second session of the conference. In this session, our first speaker is Professor Bernhard Müller from Norwegian University of Science and Technology. The title of his talk is Fluid Structure Interaction and Immersed Boundary Method for Viscous Compressible Fluid using Higher Order Method. Please, Professor Bernhard Müller.
Thank you, Mr. Chairman. Can you hear me?
Yes, yes.
Thank you. So let me also thank the organizing committee for inviting me to this interesting conference, to Assistant Professor Asif Farouk for the communication, and to Dr. Kasim for the link. Let me now share my screen. So, greetings from Trondheim, Norway, 63 degrees north. Here you see our campus, engineering campus, south of the city of Trondheim, which is on the Trondheim Fjord, which is not far away from the Atlantic Ocean. On the right, you see our main building with northern lights above that we can sometimes see here, especially at this time of the year. So the chairman said already the title. Let me motivate this because we have been doing research on obstructive sleep apnea. I'll give you an idea of that in a minute. And that was a collaborative project with the colleagues from structural engineering, from medical doctors from St. Olav's Hospital, and from SINTEF, the largest research organization in Scandinavia. The research has mainly been conducted by my former PhD student, Ehsan Khalili, co-supervised by my colleague, Martin Larsson, and I'll also present some work by my former master student, Knut Emil Ringstad. So what is obstructive sleep apnea? So usually during sleep, we inhale oxygen through nose and mouth, but it happens, especially for older males, that the muscles can relax and then the tongue will close the airway from the mouth, and we will have oscillations from the soft palate, which is snoring, but also that can close, and then we have the complete airway closed that can happen for seconds and even minutes. And these events do not supply oxygen. It is only a reaction by the brain that makes the muscles contract, and then the person can go on sleep. But if this happens frequently, this is really disastrous for the cardiovascular system. So these people are prone to heart attack and stroke. So our colleagues from St. Olav's Hospital, they want to do operations in the nasal cavity. That helps only about 1/3 of the patients, and they would like to know for whom it helps. And our task is to develop a computational tool that could do this job. Get a CT scan of the patients and then decide based on this tool whether an operation in the nose would be helpful or not. So let us look how we went into this, solving this problem. So my task was the fluid structure interaction part, and we chose to use the compressible Navier-Stokes equations as the model for the fluid flow, so that we have also acoustic effects involved, and also, if we like, also thermal effects. We used for the discretization in space, high order summation by parts operators, which have an inbuilt stability property. Integration in time was done by the classical fourth order explicit Runge-Kutto method. We have developed an immersed boundary method. I'll show you the reconstruction procedure, also a hybrid approach, and that is based on the weighted least squares method, and then also how it can be applied to moving boundaries. Then the application will be for an elastically mounted cylinder where we have a fluid structure interaction, and that is then done using this immersed boundary method. Finally, I'll give you conclusions and outlook. So first, the mathematical model. Compressible Navier-Stokes equations are here formulated in conservative form. Capital U is the vector of the conserved variables, density, momentum density, U is the velocity vector, and total energy density, E is the specific total energy. So that is internal plus kinetic energy. FC and FV are the inviscid and viscous flux tensors. In there, we have also P, the pressure, I is the identity matrix, H, that is rho E plus P, that is the total enthalpy, rho H, and tau in the viscous stress tensor, that is the viscous stress tensor for a Newtonian fluid. K appearing here is the thermal conductivity and T is the temperature. We have considered here 2 dimensions and then the X and Y components of these tensors, that is the inviscid flux tensor minus the viscous one, are then denoted by F and G respectively. Now we do a discretization of this equation using a high order summation by parts operator that was developed at Uppsala University by my former colleague Bo Strand, a student of Professor Bertil Gustafsson. I'll give you more details on that shortly. The time integration was done by an explicit method that is the classical 4th order Runge-Kutta method. So we determine the residual at different stages, actually 4 stages, and then we get a 4th order method. Since we apply this 1st order summation by parts operator twice, we do not have a damping of the high wave numbers. We do that by an explicit filter, which is 6th order and does not destroy the global accuracy of our method. So here are some details about the summation by parts operator. It is in the interior a 6th order classical central finite difference method. If you imagine this Q, this is then describing this differential operator. It is 1 over H, that is the grid spacing. H is the grid spacing. And then we have here our matrix. And that is applied to a vector that is then the approximation of our unknowns, for example, in the X direction. And if we do that for the interior, you see here the coefficients. They are the coefficients for the standard 6th order central finite difference method. However, near the boundary, at the boundary that is 0 and the 5 neighboring points, we have a different stencil, which is more complicated. It is chosen such that it is 3rd order accurate and that it fulfills this property, the summation by parts property, that I'll show you now. I'll explain that first by integration by parts for a continuous problem. The continuous problem is the linear advection equation, where A is a constant advection velocity. We consider the interval 0, 1 with an initial condition F and the boundary condition for simplicity at the left boundary as A is positive propagation to the right. We have the boundary condition 0. We define the L2 scalar product in the standard way for 2 functions f of v. This is the integral from 0 to 1 of the product f of x, w of x. The norm is then defined by applying the scalar product to itself. That is the norm squared. Now, integration by parts can be formulated in this way. So if we have the scalar product of v dw dx, we get the product of the boundary terms at 1 minus at 0 minus where we have the scalar product of dv dx w. If we use this property, and if we use also the product rule, to replace the time derivative by minus a du dx, and integration by parts, and the boundary condition, we arrive at the time change of this norm squared, which is a measure of the energy, is equal to minus au squared at the right boundary. And a is positive, so this term is negative. If we integrate over time, we see then that the energy, the norm squared at any time, minus the norm at time 0 is smaller or equal than 0. And that means that the norm squared is bounded by the norm of the initial condition squared. That means we have a continuous dependence on the initial condition. We know that a solution exists. We can also use this estimate to show that this is unique. And then we have well-posedness. So this idea is now transformed to the discrete case. And the important property that we need is the discrete analog of integration by parts. And now we come to the semi-discrete problem, where the du dx is discretized by applying this matrix that I showed you before, Q, to a vector u. And u is then the approximation of the unknowns at the grid points x0 to xn. So we have n plus 1 grid points, and then this is an n plus 1 vector. We have the initial condition f, and now we need also to define a discrete scalar product. That is done here by having two vectors, n plus 1 vectors v and w, and it is discrete is denoted by this subscript h. So that is the grid spacing. So then we have the grid spacing h times the v transpose times a diagonal matrix h. That is convenient if we want to have that this, sometimes we need that this matrix has to commute, then that is easy, times w. And then the discrete norm squared, the h is here missing, is then the scalar product applied to itself. Now we can then require or define the summation by parts property, which is then, as you see, completely the discrete analog of integration by parts. So then we have the scalar product of VQW, which is the approximation of the W dx, is equal to the boundary terms. N is at the right boundary, minus 0 at the left boundary, minus where we have the scalar product QV of W. So complete discrete analog. And then we use the same technique as we used for the continuous case, for the discrete case. And by that, we get this estimate for the time change of the discrete norm squared, which is our energy measure. And if we implement the boundary condition properly, I skip this part, then we get a similar estimate as for the continuous part. That means that the discrete norm at any time t is bounded by the discrete norm of the initial condition. And that means stability. So we build in this summation by parts property in our differential operators. So let's see. Now let me tell you about the immersed boundary treatment. Instead of using body-fitted grids, we use Cartesian grids. The reason is when we have complex geometries, grid generation is quite difficult, especially when we have moving geometries. So the idea is to use Cartesian grids and to represent the solid bodies moving, being deformable or not, on this Cartesian grid. Let us take an example. Let us take an elliptic body that is then immersed in this Cartesian grid. What we do is we determine for each point, for each grid point, whether it is a fluid point or a solid point. So this ellipse here is our solid, so B having one intersection, and we use the ray casting algorithm for that, having one intersection with the boundary, then we have a solid point. Here we have two intersections with the boundary, then we have a fluid point. So we can do that, and then we can flag these points. And here we have the flagging for the fluid points. They are the blue squares, and the solid points are the red circles. We want now the values, the solid points close to the boundary to carry a certain information so that we can do the standard finite difference operations for all the fluid points. So that means we will mark the ones closest to the boundary as ghost points. And then at the end, we have then a flagging of fluid points, of ghost points, and of solid points. Now we want to give these ghost points a meaning. We want to give them values such that they reflect the presence of the boundary, of the immersed boundary. Let us take an example here. That is the point that we have here. That is a ghost point. We determine the normal through the boundary that is going through the ghost point. So here, this normal. And the intersection is the body intercept. And then we get from there to the fluid domain by mirroring the normal at the body intercept. By that, we get to the image point. And the image point is now inside the fluid domain, so we can interpolate its value, knowing the values of the neighbors. So we do that by bilinear interpolation. So then we know the values at the image point. Now we apply the boundary conditions. We use Dirichlet boundary conditions for the velocity. We have the no-slip condition. That means that the velocity of the fluid is equal to the velocity of the solid at that point. And that value of the solid velocity is either given if we have a prescribed motion, or it is computed when we have fluid structure interaction. Then we simply express the value at the boundary that we know as the average of the values at the image point and the ghost point. That is a second order approximation. Neglecting that error term, we get an equation to determine the ghost point values for the velocities, x and y velocity, u and v. Neumann conditions do we have for an adiabatic wall? The TdN, normal temperature derivative, is 0. So, and we also use the boundary layer approximation for the pressure for dPdN is 0. Then we approximate these derivatives at the body intercept by a simple central difference approximation, which is second order. Again, neglecting this term, we see then that the temperature at the image point is equal to the value at the ghost point. Thereby, we get the value at the ghost point. So we get the temperature there and the pressure. So at the end, we have determined the velocity components, temperature and pressure at the ghost point using this technique. So to approximate the first derivatives at a fluid point next to the boundary, we have a stencil that needs 3 points to the left and 3 points to the right. In our case, we have the 3 points to the left as fluid points, 3 points to the right, we need ghost points. So we do not need only one layer of ghost points, we need 3 layers. So we get them in a similar way. We determine the normal through the ghost points, the body intercept, and then the image points, and then we do the interpolation to determine then the values at the image point. Here in this case, for the first ghost point, we have a technical difficulty because we don't have 4 fluid points surrounding it. We have only 3, but we can use the boundary condition at the body intercept to get us the 4th condition to be able to interpolate the values at the image point. So that is the standard way, but we have also another way, a hybrid way, where we do the same procedure as I just explained for the second and third layer of ghost points. But for the first layer, we do something different. We use a weighted least squares method. We have a couple of points in the fluid where we know the fluid point values of velocity, temperature, pressure, and we get an overdetermined system. And then we solve a least squares problem, which is weighted by the exponential with the distance to the body intercept squared. So then we have another way of determining then the values at the first layer of ghost points, because we determine then a polynomial and then we evaluate that polynomial at this first layer of ghost points. How do we compute the viscous fluxes? There we have derivatives involved, ux, vx, tx, for example, also in the y direction. We do it by applying the summation by parts operator for the first derivative. So we come then from the fluid domain, which is in that case here to the left. It continues further to the left. And to the right, we end with a third ghost point. And then we apply this operator on that line, and we get approximations to the x derivatives in this example. And then we can evaluate all our terms in the viscous flux and then apply the standard operator for a sixth order to evaluate the x derivatives in this example. For the y derivative, we do it similarly. Here is an application of this approach to a steady state test case, flow over a circular cylinder at Reynolds number 20, Mach number 0.1. And we used then this hybrid method where we use the weighted least squares for the first layer of ghost points and in the bilinear interpolation at the image points for the second and third layers of ghost points. Here we used the finest grid as a reference to evaluate the errors. Here you see the grid spacing H, here you see the errors and the slopes, second order is given here, third order is given here for two norms, L2 norm and infinity norm for U, V, rho and P. Rho is the density, P is the pressure. And we see that we get for both norms, we get a third order accuracy. So that means this method that is sixth order in the interior, fourth order third order near the boundary, and then using this approach that I just explained for the immersed boundary method ends up to be third order accurate. Here's an application now to our problem of sleep apnea. That is a patient lying on the back. Here we have the nose, nasal cavity, and the pharynx. And that is our patient 12, whom we investigated quite accurately. We got CT images from this patient from our colleagues at the medical faculty at St. Olav's Hospital, Mats Moxnes and Ståle Nordgaard. And out of that, my PhD student Ehsan Khalili focused on this part of the pharynx. We got the data of the geometry that was retrieved then from these CT images from our colleagues from structural engineering, Hongliang Liu and Björn Skallerud. And then Ehsan did a computation by putting that into a Cartesian grid and applying our method. And here we see a simulation that shows then vortex dynamics that is developing behind the constrictions. Here, that is the soft pellet here. And here is further down, it is near the epiglottis. The geometry is slightly simplified to get it convex, because if we have a non-convex problem, then we have difficulties to accommodate our large number of points that we need in our stencil. But for this problem, this works. Now, moving boundaries. In moving boundaries, we have the problem that points that were previously ghost points might become fluid points. Here we have such an example. This would be the boundary at time level n. This the boundary at time level n+1. Usually we don't move it that far, but in this example, we assume that we know already the values at these two points, and that one was known from the beginning. How do we get then the values at this freshly emerged fluid point? It was a ghost point before, so we have no proper time history of that. That is solved in the following way, that we use the body intercept for that particular point to give us the boundary condition at the boundary of the solid. And there we have the boundary conditions. We know the velocity. We know then by the pressure and the temperature. So we have data that we can use, and we use that then to get values for the at this point n. So in that way, we can then handle freshly emerged fluid points. The application is done here for an inline oscillating circular cylinder. So initially the fluid is at rest, and then the X component, that is the center of the cylinder, is moved with a frequency Fe, that is the excitation frequency. We have some amplitude AE, and we determine then the Reynolds number based on the maximum velocity that we get from this. And the Kurgan-Carpenter number is this velocity, that maximum velocity non-dimensionalized, using the product of the diameter of the cylinder and this excitation frequency. That is a low Kurgan-Carpenter number, which is the ratio of the nonlinear acceleration to the local acceleration. The Mach number is low. Here you can see the vorticity for this problem when the cylinder is moving back and forth. And on the right, we have the pressure. That is the pressure relative to the stagnation pressure. And to the right, we have the acoustic pressure, which we here identify as the difference between the instantaneous pressure and the average pressure over one period. So that is the advantage of our method, that we can also get acoustic information. Here we have the validation of our approach by comparing with experimental data at certain locations, at certain X locations. Here, in the left figure, the velocity in X direction U is compared with experimental data. Our results are the lines, and the experimental data are the symbols. So you see there is general good agreement. The same is true for the velocity in the Y direction, V. And the data here are obtained from our colleagues from Erlangen University in Germany. Now, fluid structure interaction. We have here considered a coupling of an elastically mounted circular cylinder in uniform flow. We describe this coupling by describing the mass spring damper system, where ms is the mass of the cylinder, b is the damping, and k is the stiffness. The positions and velocities of the fluid of the cylinder surface are determined by the positions and velocities of the cylinder. So here that is given. So S is the center of the circular cylinder. And then just getting the values on the cylinder, we have then the angle phi here involved. And the velocity of the cylinder, that is xs dot, that gives us the velocity of the fluid at the cylinder. And that is the no-slip condition. So the location and the velocity of the cylinder prescribe the boundary conditions in space, so the location and the velocity for the fluid. On the contrary, the force acting from the fluid on the structure describes the external force that is here on the right-hand side of this equation describing the mass spring cylinder system, the mass spring damper system. And that force is given here. It is the force exerting by the pressure force and the viscous force. So that is then our coupling. The solid prescribes the location and the velocity to the fluid, and the fluid gives the pressure acting on the surface, which is then the external force for the mass spring damper system. We applied this to a problem from literature, and that is for a Reynolds number of 200, a Mach number of 0.25. The ratio of the solid to the fluid is 4/pi, and the non-dimensional velocity, the uniform velocity, there we use the natural frequency Fs and the diameter of the cylinder. The damping is non-dimensionalized using the stiffness K and the mass of the cylinder. And we have this value that was in coincidence then with the literature. Because we have data, numerical data, from a simulation based on spectral method in an accelerated coordinate system by Blackburn and Kaniadakis, and an immersed boundary method by Young and Stern of an incompressible immersed boundary method. So we see here some comparison, that is the location of the center of the cylinder with different grid sizes by Young and Stern, and the circles by Blackburn and Kaniadakis. And our result that was obtained by Knut Ringstad in his master thesis, that are the red crosses here. And we see here it's not completely converged, otherwise there should not be this little gap here. But otherwise we are quite in good agreement with the data from literature, especially for the y velocity. That is really on top of what we have from literature, while for the velocity in x direction, u, there is some discrepancy. You see also the values are smaller. Then we have some shift also in the where the location of the cylinder is. Now we analyzed also the power transferred from fluid to structure. And that is essentially the product of the force, the scalar product of force and velocity. So here we have that surface integral over the cylinder with the pressure involved, the normal velocity, the viscous stress tensor velocity, and then the normal velocity, the normal vector. And that can also be expressed as the scalar product of the velocity vector u and v, and the drag, the vector of the drag and lift forces. Now we analyzed these terms individually to see what are the contributions then of the power transferred from the fluid to the structure for this contribution UFD. That is shown here. So then we can see in which phase of the motion of the cylinder there is energy transferred from the fluid to the cylinder. And we see here it is largest at 1, that is when the cylinder crosses the origin, and then kinetic energy from the fluid is transferred to potential energy of the spring. And vice versa, it is at 5, that is when it is moving back again, then energy is transferred from the spring to the fluid. For the y direction, it is a little bit more complicated because the lift changes sign. It is 0 at positions 1 and 8, so that is here and here, and it gets large here between 2 and 3, and that is here we see it when the cylinder is moving to the right before it comes to the position where V gets 0. And the opposite, the energy transfer from the cylinder to the fluid is here between 6 and 7, or at 7 it's most negative, and that is when it is moving down again. So that is giving then us the possibility to analyze the transfer of energy per unit time between fluid and structure. So let us then get to the conclusions. We have developed a ghost point immersed boundary method for the compressible Navier-Stokes equations, employing high order summation by parts operators, giving us inbuilt stability. We applied this immersed boundary method to compute steady and unsteady flow problems and demonstrated its accuracy. We also demonstrated the versatility of the immersed boundary method by simulating flow in the upper airways of an obstructive sleep apnea patient. That was a 2D simulation. We applied the immersed boundary to moving boundaries, verified and validated the method by simulating an inline oscillating circular cylinder. And finally, we verified the immersed boundary method for fluid structure interaction of an elastically mounted circular cylinder. The outlook: we want to extend this immersed boundary method also for flow over non-convex structures. That is important because of the complex geometries in the upper airways. And of course, we want to extend that to method to 3D. Then it is planned to apply the 3D immersed boundary method in our new part of our research project, in our interdisciplinary research project on obstructive sleep apnea to fluid structure interaction problems in the upper airways. And of course, we want to improve the resolution by adaptive mesh refinement near the immersed boundary. Let me thank the funding agency, that is the Research Council of Norway, and acknowledge my former PhD student, Isan Khalili, and master student, Knut Emil Ringstad, with their PhD thesis and their master's thesis, respectively. Thank you.
Thank you, Professor Bernhard Müller, for this such a nice talk. Now, question and answer session. Audience are requested to ask questions, please.
Professor Mustafa, you can ask a question, please.
Thank you, Professor Müller, for this nice talk. It was very interesting. I hope you can solve my wife's snoring problem by your technique.
I hope we could, yes.
I'm just wondering whether your method is too costly. So how what about the computational cost?
Well, yeah, thank you, Professor, for your question. This is very relevant. At the moment, this method is quite time-consuming because we are solving the compressible Navier-Stokes equations with an explicit method. So we have the CFL condition, which is severe. So we need many time steps. So this is costly, and I think we used for the simulation that was for the elastically mounted cylinder something about 100,000 grid points, and that took a couple of hours on a cluster. So we have used message passing interface, MPI, and we use a cluster here at our university, the Norwegian University of Science and Technology. So it is costly, but our goal is to get insight. And once we get that, we hope we can simplify things and get in the end a tool that the medical doctors can use to decide to do an operation, a surgery in the nose or not. That is our goal. So for the moment, I would recommend for your wife to use or to ask her doctor maybe to use CPAP, that is continuous positive airway pressure mask. I know this is uncomfortable, but I have a relative using that, and this keeps the airways open by a positive pressure, but it is uncomfortable to wear this mask during night. But otherwise, I hope we can supply a tool at the end of our research so that you could, that the patient could take a CT scan, and then we get the data, do the simulation, and then decide doing a vertical surgery, so on the computer of the nose, and see whether that would help the flow through the nasal cavity and down to the pharynx or not. So that is our hope.
Thank you, thank you, thank you.
Any other question, please? Okay, if there is no question, I thank again to Professor Müller for such a nice talk. So, Dr. Asif, may I proceed further?
Yes, please, go ahead.
Okay. Our next speaker is Professor Irfan Shayab from Turkey. So title of his talk is Skew Cyclic Codes over a Finite Non-Chain Ring and an Application. Professor
Thank you,
Irfan Shah.
Professor. Can you hear me? Can you hear me?
Yes,
Yeah,
yes.
can you hear me? Okay, great. Okay, thank you for your invitation, and I'm happy to give a talk here. I'm going to talk about a paper which is a joint paper with Cruz, Keitik, and Chinat Pilaya. However, I have designed it so that some, mostly can be followed by the participants, given the fact that we have a range of areas here. So the motivation is as follows. This is mainly about algebraic coding theory, which involves the theory of communications. And we are going to talk about the binary larger alphabet, non-commutative rings, which is a very recent topic, and our talk is going to be over a non-commutative ring over coding theory. Skew is specifically called skew codes, and as family of skew codes, it's skew cyclic codes. And I'm going to introduce the ring that we have studied and an application to DNA codes. And hopefully I'll be able to conclude my talk. Okay, so the ring here is a quotient ring with 3 variables that we are going to attack, where we have u, v, w with the specific constraints. U squared is u, v squared is v, and w squared is equal to 1, and u times v is 0. Okay. So what is coding theory about? We have a message, we want to encode and send it in order to see if there is any error involved. But this is happening in real life situations because all our messages are going through specific channels. And then after we got the message, we check it, and then we correct it. If there is an error or not, we convert to the original message. This is not a cryptography. This is just error correcting, meaning both sides know what they are going to expect. Nothing hidden. The point is to fix the error, to find and fix. So we need a set, universal set. This is a nice picture. And then in this universal set, we are going to pick or code words. Like, we speak English, you have the words in English, and you have all words, say, of tuple n. So the red ones are meaningless, but the green ones are perfectly well-known, legitimate English words. So if an error happens, normally would accept to be not to be too far. So here we have a 1 radius or t radius balls where the error will deviate from the original code word if it happens. So basically, you need a set, you need a subset that we are going to call code, and we need a metric. And this metric is going to distinguish between the words and code words. So that's the idea behind it. And the English alphabet, English word thing really makes sense if you want to think that way. So if you have a metric, then you can decide how good or how bad your code is, basically how many errors it can correct or not. Basically, if you have the minimum distance 2t plus 1 or 2t plus 2, odd or even case, then your code can correct the errors and detect d minus 1 errors. This is going to tell right away the ability of your code. But defining the minimum distance in a nonlinear nonlinear problem. It's an exponential problem, NP problem, non-polynomial problem. So it's a very difficult one. Okay, meaning if you have a big set, which is impractical the use of this kind of situations. Okay, so if we bring down to the very familiar, we have a field FQ with Q elements, where Q is a prime power. And we can think of a code as being a linear subspace, which every one of us know from linear algebra. Then you have the dimension, which is going to give you the size of the set, and you have the length of the code, which is the length n here. And the only thing that remains to define a metric, and the very familiar and most common one is the Hamming metric, where basically first we start with the Hamming weight, meaning you have a code word of length n, and you just count the places where the entries which are non-zero. and that's going to contribute to the weight of the code word. And among the all non-zero weights, the zero will be there because this is a linear space. So among the all non-zero weights, the minimum one will give you the minimum distance, Hamming distance. And when I say Hamming, we can think of different metrics, which is going to be the case in our study, and we are going to relate to the Hamming code in reality. Okay, so you have three parameters: the length of the code, the dimension, or the size if it's nonlinear, and or if it's not a linear subspace. I mean, if it's a module, then we're going to define the and the minimum Hamming distance. Okay, so if you go back to our picture, really, this is a very difficult problem because you want to have t large. If you push t to be large, it's gonna touch to the other ball. Then we are not going to be able to decide which one is closest if an error happens. So this is also a very difficult problem. If you want your code to be large, then the minimum distance has to be small. If you want minimum distance to be large, then the size will be the small. So there is an optimum problem going on. That's why, we are searching and working on this topic. So basically, in general, if you have a ring R, could be non-commutative. So we can think as a module. If it's non-commutative, which is going to be the case, we can think about left R module. Could be the right R module as well. We want code words to be added, to be closed under addition, and to be closed under scalar multiplication. Okay, and I talked about Hamming distance, and the minimum distance of a code again will be the non-zero, x not equal to y. So the non-zero weights, minimum distances or weights. When we have a code linear, the distance and the weights, minimum weight and the minimum distance are the same. They collapse to the same number. Okay, and we have a notation here, which is the length, which is the dimension if we have FQ field, and D the minimum distance, and Q tells us about the size of the field that the code or linear subspace is defined. And again, as usual, we can define the dual of the code with respect to an orthogonal to an inner product. And here it is the familiar one, meaning we multiply component wise and we add them up. The only difference is if you are in the field, things working as a modulo P if Q is a power of P, so modulo the characteristic. That's what's happening. And if you are in a ring, it depends on its characteristic as well. Okay. So here is a nice example. This is Hamming code, and it's used in computers, in the memory. So it's perfect, meaning nothing. If you take the one radius ball around any legitimate code word, so the green ones are legitimate, we use them, okay? And really, this is a binary expansion, so I have transformed into decimal. They are just the real ones. This is the whole space, length 7, subspace. This is one perfect error correcting code. So if an error happens, say if you receive 34, we are sure that this is 42, okay? So we can always correct one error. If there are more than one errors, then it's not gonna work. Usually we have such a question, which is a nice question. So we do not guarantee that we can correct any errors. We have the capacity, so we rely on the hard way, or we have some assumptions. Or if you can use this code word, if you are not facing more than one error, then this is going to be perfect. That's what it means. Okay. So what is the deal with this? Even in the field case, we have too many subspaces. This is the Gaussian number. We can remember this one. So this is exponential. So we have too many. So it's not easy to write down to list the subspaces and then pick the one which has the highest minimum distance capability. And what's happening really, error correcting codes nowadays are used in post-quantum cryptography, which means that we need such things so that quantum computers cannot decrypt it. And linear codes, coding theory has come into play, interestingly. Okay, so now, as we can imagine, the very first example was the binary codes, and still use them, which is what we are doing. But we would like always to have larger, if possible, rings or fields, and then come back to the binary, I mean, project down and understand it. And in 1994, this is a milestone paper by Hammonds and his colleagues. They picked a Z4 module, submodule Z4, and then they used a map, gray map. We are going to hear about this, and map it down to Z2 or F2. So what was good? We have a linear and nonlinear codes, but nonlinear codes do not have the structure. And the very famous nonlinear good codes are curved, perforated glottals, and some others are shown here to be maps of linear or submodules over Z4. That's interesting. So you go up somewhere, you have a nice structure, you pull it down, no structure. So yes, you can still navigate between these two spaces and get some information about the non-structural property. So this is a very famous one, and things from this one become really interesting, and people started to work on codes over rings. Okay, and this is another nice paper, and early papers. There are many now, but since 2007, there is another paper which considers skew non-commutative rings, but cyclic. And this is also important because, as I told before, we have a huge space of linear codes. So some of them are linear, some of them are nonlinear, and in the linear, some of them have structure specific, some do not. But with the skew part, we still can pick linear, but linear ones which are not studied before. And that's also very important. And since this paper, there have been, and today we are going to see a work on this specific area, meaning using skew structure to study codes. Okay, so what is cyclic code? Cyclic code is a linear code first, but when you do the right cyclic shift, it closes, it's invariant. So it is inside the set again. So under this map, it is invariant, the C. So here is an example, with ternary as Z3 or F3 with n tuples. So this is a linear code, but more than that, it is cyclic. You can shift, right shift, you can see it's closed. So this is, but they are not cyclic, and we have a cyclic code. So we only need the structure to be invariant under the right cyclic shift, circular shift. Okay, and this is also in practice very useful. Engineers are using this kind of structure, and the fact is gonna come right away. So if you have a code word or space which is closed on the right cyclic shift, algebraically, this is a quotient ring, polynomial ring. So we take an n code word, we map to a polynomial. Since with respect to multiplication, being right cyclic shift, it means when you multiply by x to the n becomes 1. So really, we are working under a quotient ring. And having this in mind, the next thing will be, we're going to see, which is the case, this is not just a subset now, it is a cyclic code is an ideal in this particular ring. So being an ideal will give us tools, algebraic tools to understand it better. And what is also important that the very famous codes used today, Reed-Solomons in CDs and other place, Golay codes, quadratic grids are all cyclic. These are all cyclic codes. Okay, and having a cyclic code, as I mentioned, it's an ideal, and the ideals of this quotient ring are all principal. So it means that we can just pick a generator and a polynomial that's going to help us to represent all space, all ideal, all code. So, and G is not just random, it has to do ix to the n minus 1. So we'll have a structure, and further, by reading its degree, if it's R, for example, you can tell the dimension. And also, further, you can list all the code words by using this G only. So very first and very minimum advantage is that in order to list all code words or bases of code words as a linear subspace, you can just pick a polynomial, put into a computer that's going to represent the whole thing. So if you have, say, 25 basis elements, you pick a polynomial or specific degree and you are done. So it saves time. And if you have this polynomial, you can exactly write down, the generator matrix. These are the bases, and write everything down. You can go back and forth. Okay, and now we go back to the skew polynomial ring, and we can find information. This is a nice book regarding the non-commutative case, because there are challenges over there too. So in order to define this ring, first let me give an example about a map that should be. We need an automorphism really. So field automorphism. If we pick F4 with this particular elements where alpha is not in Z2, but it has a specific constraint, then the famous automorphism will be the Frobenius automorphism, meaning taking the characteristic of the field. And the polynomial will be defined, the Frobenius map is defined over the extension 2. Okay, so what's happening with this skew polynomial ring? The only thing which we need to understand is basically when you multiply polynomials, we multiply the terms. So when you have ax to the something times bx to the something, this is just a multiplication. Then in order to take ax to the I to the right-hand side, change the places, we need to apply the Frobenius map I times, depending on the power of x. So this is what we need to pay when we put into the right polynomial form. And here is an example. Again, we had this F4, which just mentioned before. So the map was taking a to the a square in general, and that's the Frobenius map. And if you apply this map, here is a small algebra here. So we want to switch x and alpha square. You gotta multiply theta once because it's x, and then you look at the map, you plug in. So it is troublesome. It's not very straightforward. The next thing is, what do we know about this quotient ring? Polynomial ring. Then we are going to need the quotient ring too. So because now again, if we take the coefficients from a field, then the degree still works up to some sense. Okay, as we can see, it's not equal. Normally it was equal before. Okay, so in general it's not equal than the maximum, but if you multiply, still equal, because in this skew field still we do not have a zero divisor property, so we are safe. So we have 3 and 5 degree polynomials. You multiply them, you get an 8 degree polynomial, has no zero divisors, and the units also are the units of the f, really. Okay, there's a typo here, should be units of f. And we can divide, but we need to keep the orders right. So we are given a right division algorithm. So meaning if you're gonna divide G by f, so f is going to be in the right. So you keep the order of division, everything is the same, I can say. If you keep the order of division, you can do as you were doing with the polynomials over commutative rings. Okay, here is an example. We have a skew polynomial, and x minus alpha squared is a right divisor here. It's not telling much, but the important thing is that, as you see from here in commutative case, alpha squared would be the root of the polynomial. However, if we have a skew polynomial field or skew polynomial ring like this, you see alpha squared is not anymore at 0. So it has its own difficulties. Quite. Okay. And then we would like to know the center. The center can be, we know it again from the book of MacDonald. And if you have a map, Frobenius map with order m, then any power, and then all polynomials with the powers of m, or dividing m actually, are lying in the center, because this map will leave them invariant. Okay, and we can tell about the ideal, really, just repeating the same thing, I guess. Okay, and our interest will be on the quotient ring over this skew polynomial. And specifically, in order this quotient to be defined, that is important, You can't just go ahead in a non-commutative case, pick any ideal and just put it there. It has to be two-sided. And especially we are going to work in this one, x to the n-1. Let us recall the cyclic shift thing, because we do use it. And that's what it means being skew cyclic. So this n here, the order must divide n. So we have a restriction. It's not going to work for any length, I say, for any n. So it has some restrictions. Okay. And so what do we mean with the cyclic code? Basically, it's quite the same as cyclic shift, but this time when we do the cyclic shift, we impose the theta. So not only taking the cyclic shift, but we do take the theta values of all entries. That's the difference. But if theta is 1, I mean, it's identity, right? Then we got the cyclic codes. So this is a generalization of the cyclic codes. That's what it says, actually. Okay. So again, if you do this algebra here, and if you just take a code word with a polynomial, if you match them, then this multiplication is going to be an ideal again in this particular non-commutative polynomial ring. So that's what the Butcher and his colleagues really put down in the paper in 2007, which made us and many researchers going after the skew code case. Okay, and everything here, if we are going to take, but we need to keep the order right. So we're multiplying from the left, and the divisor are from the right. So when you multiply from the right, we can divide by x to the n-1 because the division, long division, works from one side. Then any polynomial could be put into less degree than n all the time, as it was in the commutative case. And 2009, me and my colleagues, we studied the left modules with respect to this polynomial, non-polynomial rings also. Okay. Okay, now I did mention about theta being identity, then you get the usual thing. Okay, and ZP are not interesting. You need the extension fields because then you're going to have automorphisms. And there have been some new codes, record-breaking codes over this particular class, non-commutative rings. So it makes it interesting to study. And the factorization is not unique. We are going to see in a moment. So this means in a commutative case, it was unique. So we had an amount of codes. Here we have plenty. Here is one example. You pick the field F4 with 4 elements, and only we look at x4 minus 1. As you see, we have quite many ways to get different factorizations. What does this mean? Basically, if you pick any, say 2 degree, like this one here, or maybe I should, since we were talking about the right, I'll pick this one from the right-hand side, call it G. So you make this code, skew code. You get a new code word. You can pick another one. So you see, in a commutative case, you have just x squared plus 1, really. This is, as I said before, it includes the commutative case. So besides this one, you have plenty choices to construct new codes with the same dimension. Normally, they are linear. They have a structure. So linear, but in skew, they have a structure. That's the advantage. And now our work is over this particular ring, which is a generalization of many, sufficiently many, I would say. It's a generalization. It's a quotient ring. And we'd like to look at the structure of this and define codes over this as a skew cyclic codes, non-commutative. And then at the very end, if time permits, study the structure of a specific family codes defined over this particular ring, which are called DNA codes because they resemble the DNA structure. Okay, so if you pick this ring and if you take Q to be characteristic, this ring does change into 2 parts. If characteristic is odd, it decomposes into 6 parts, direct sums, over a finite field FQ. Basically, this ring is an extension of a finite field FQ. So This is a little bit more natural and more easier part, I should tell, because you have the idempotence. After you have the idempotence, theoretically, you can say that I have 6 copies of the field and I'm done, which is the case. Okay, so, but in the even case, we do not have a direct decomposition, but it still decomposes up to a point. So we give a name to this ring, which is a chain ring over FQ. And what is good about this chain ring? Okay, if Q is, because Q is even, that's the point. Meaning you cannot factor W squared minus 1 into 2 linear parts. So you have a chain, and the chain looks like this. Okay, and then the original R, the ring does still decompose into 3 parts, each part being isomorphic to this one. Okay, so this is also good. And the problem will be, how much do we know about this ring? And there are some recent studies and familiar studies done before. Okay, so now, again, we define the theta quite natural, actually. We borrow the one from FQ, and we just, we keep U. I'll just explain quickly, UV and W invariant, okay? These were the new extensions over the ring, over the field. So we keep them invariant, fixed, and then we just play with A and B. These are the coefficients of the elements of the ring. So they do change with the Frobenius map. Again, here we can divide. We can define the quotient ring. Okay, so it becomes an extension of the original quotient ring over FQ x modulo x to the n minus 1. So we are introducing ring elements to the extension. That's what's happening. Okay, and also we borrow some properties from this particular base quotient ring. Okay, so again, we define the cyclic code. I'm not going to repeat. Then we can define the dual and self-dual if it's equal to itself, and self-orthogonal if the dual, if the code is inside the dual. These are all pretty straightforward, just definitions, extensions. And also the interesting part is, I may have not mentioned before, but the dual is not just only a linear code, it is also a cyclic code. In this specific case, it is also a skew cyclic code. So they are like brother and sister, as we would expect. Okay, and then now we need a map. So we have a large extension up there sitting, and down we need to have a map, as in the original paper, to bring it down to the world so that we can understand it. Okay, so, and this map is defined by the help of the decomposition that we had before. So in our case, we had 6 components, if we can recall it, and then we can just take the representative of them. And each Ri, the coefficients are in FQ. So basically, if you have the ring R, you bring it down to the field case with the 6 copies, and you have this gray map. This is called gray. I mean, we call them gray map. We credit the very first definition of the skew. I mean, not the skew, but the ring case. And also, if we are in odd even case, sorry, then these are also the coefficients of that decomposition. So basically, we have a gray map we bring down to the Hamming weight. That's what's happening. So we can talk about things down in the earth, and the minimum Hamming weight or minimum gray weight are defined in the usual way. So we have maps that bring or quote to here, to quotes over FQ, meaning fields. Here, the quotes over the chain ring. So we cannot go further, but still we can if you want to, but the structure may not be hold true. Okay. And the decomposition of odd case to cyclic quotes of 6 copies, the decomposition of the even case to cyclic quotes of 3 copies. Okay, and the natural, what happens to the dual of this? We can answer those questions quite easily, I should say, because of the fact that if you have the duality, okay, holding through, then you can take the C and you can look at the copies. Both, this is the odd case, and this is the even case. The parentheses are for the even case. So we have two terms inside packed together. So the dual is going to be just the copies of all the duals of each part. It's similar here for the even case. So we can say, and in a very recent paper, there is a fact, there was a work here. We do not, this is a, should say, some sort of generalization, but they have shown that the images of these codes are not cyclic really in over the ground field or the ground or FQ, say IPQ. They are quasi-cyclic. So they have blocks, cyclic blocks put together, lined up together horizontally. Still a structural thing that we know in the field case. So we can, what does it mean? If you go back down to the gray map, down to the fields, or we are going to end up with some structural or quasi-cyclic structures. And in our case also, we showed that this is true in our case too. We have special quasi-cyclic codes over FQ and over the even characteristic, I mean over RW. Okay, I know my time is running. I'm not going to go further to the structure, but for each case, we have find the generators as a modules. Okay, we have determined them. I want to go to the DNA case a little bit, if time permits. So all the structural generators and everything are all, all are established in this paper. So let me talk about the DNA case, which is an application of the even case in our work. So a very famous property regarding the DNAs is that they match together before they replicate. So up to one point they match, they got the energy, and then they split. And this matching is interesting. They match, C is matched with the G, A is matched with the T in order to replicate. If there is enough sufficient good matching, then they split up. So slip up into two parts. They numerate. So basically, here there is a checking. So the cells are checking, making the checking, error correction. What does it mean? It means that if they don't have enough equal matchings, they will drop. So it means the cell will die. It's not going to replicate. This is a good thing. It's happening in our system. And unfortunately, the bad thing is if they mismatch and still reproduce, that's like, diseases like cancer, blah, blah, blah. It's a bad thing. So what happens in 1994, Leonard Edelman, the very famous Hamiltonian path problem was solved by putting DNA nucleates in the problem, and just in a fluid in a bio lab, they just in a second they matched each other. The problem was solved, and the problem was to he put the things accordingly so that they can match. And this was very important to use biological DNA computing. This is the start of DNA computing. Okay, I told before, for us, it is this very famous property, which is called Watson-Crick complement. Always A and T, G and C do match each other. Okay, and this is a matching. There is a direction from 3 to 5, and the matching is in the reverse order, as you can see. It's the reverse with their counterparts. Okay, so A and T, C and G, C and G, T and A, G and C, A and T. Okay, so now, what we are going to do now? What we are going to do? We are going to do the following. We want to have codes actually, so that they resemble DNA. We don't have much information to tell the truth. Okay, we are just Watson-Crick complement property and the reverse complement property. So we impose these two restrictions into cyclic codes, and then we say, well, how do the structures look like, and how do examples look like? So the optimism here is that if we can get closer to DNA structural property, we will have a better chance to correct errors. Okay, so the very first study was about the FW really. And I recall I have done some work on this papers about this one. So, I mean, the very first one was about 4 alphabet from some other, I will mention most of the papers from other scientists, researchers, and then, we would also resemble to this 4 element. And this is going to be the base of our study here, because our study, if you just recall, over the even case, in the base, we had this ring, FW, the chain ring. But what's happening now? Normally, here's an example. If you have a length, I don't know how much, but a length, particular length code word, then if you reverse it, this is how it's going to look like. So if you have one-to-one correspondence, they will be the same. But if you have like here in this particular ring, we have tuples, I mean doubles, represented by ring elements. That's what's happening. Okay. So if you reverse this process, the reversing will not be the same, will not gonna hold. So, and here, example, if you pick randomly, if you match this AA, 3A and 1C, this one, with the ring element from this particular ring, then its inverse will be CTAA. Basically, it's not going to correspond to, or CTAA with this element. Okay, we have two matchings, and another one. Okay, we have three matchings. Then, if you combine them, like 4 here, 4 here, and 4 here, and the respective, and this one, 4, 4, and 4. So now, if you write the reverse, they don't give the reverse. It's not the reverse of this one. So what I'm trying to say is, if you match the elements of this, let me call A, with the elements of the DNA straightforwardly, as we have to, because we want to go to the alphabet back from the ring. So we are not going to succeed if you go ahead blindly just match them, because the reverse of the ring elements will be different than the reverse of the alphabet. So there is a reversible problem here. It's a matching problem. So in order to succeed this in 2015, me and my PhD student, actually she came up with this table. She worked harder, and she could put down this table, which gives a matching between the alphabet, double DNAs, and the field elements. And this one preserves the switching, the reversing process. So we make use of this one, this property in our study also here. Okay, so I guess I have only a couple minutes left, and let me just go a little bit further. So this one is the base map of what we have of our ring, sorry, base field, I should say. And remember, we are attaching U, V, and W to extend this to this ring. So we first make sure that we have a map, taking this field elements or two S tuples here to this one, to the DNA alphabet. So we used, again, and go back to the table, we used this one. This has a generalization over F to the 4 S to S. It has a generalization, further generalization. So we do use that one to guarantee that things are going to be okay. You want to make sure. And the map here is again over this ring, which is an extension. It's going to be the, again, order 2 map. This is an order 2 map. It's a Frobenius map. It's mapping only the field elements as we used before. So everything now goes smoothly. The only thing is left out is to guarantee that if you pick a generator, specific generator, not any, for a cyclic, skew cyclic code, that generate after taking all polynomials, we are going to be sure that the reverses are going to be there, reverses of the original, I mean of the DNA, because the reverses of the ring could be satisfied, but then we have to map them to DNA. That's where this table maple plays a role. Now, with this specifics and the map, we are good. We can do that. This is work about it. So another lemma which says if you pick 2 polynomials, f and g, This is basically W bar is W plus 1. The characteristic is odd, so it's the same as W minus 1. It's a cyclic code, ideal, in this ring, with the properties as in theorem. So the properties are here that G and F are self-reciprocal polynomials, meaning if you reverse the order, they are the same. Okay. With n even, the order of theta is 2, and both have degrees odd. And further, suppose that F and G are theta reversible, then the code is theta reversible. And being theta reversible gives a candidate for the DNA part. And here we have looked at odd parts, but even parts may be of interest for further study. So this is an open question still that we are considering. How can we manage that one? Okay, and that's also the main theorem says that if you have everything as in lemma, and if you use the map defined before, then we'll be sure that the image to the alphabet, DNA alphabet of this code will be a DNA code. Okay, and in general, we have a Grismer bound. Here, I'm giving an example before I'm done. Actually, I already am 1 minute, I think I had, if I have not mistaken. Okay, if you take this polynomial, this is a theta reversible polynomial. So you reverse it and you apply theta, you get the same thing. That's what it means. And then if you pick F and G, particularly G is this one, you pick an F like this, and you make sure that it contains all code word, one code word, all one code word vector. Actually, this is a code word. So C generates a DNA code of length 6, distance t. It's a small one, and minimum distance 3, minimum distance 4, dimension 3. It satisfies the Grismer bound. It's an optimal code. It's the best one. It's not a breakthrough, because there are small ones, but it encourages us to look at it further, to study it further. Okay, and this is the very last theorem, basically. Since we managed to understand this ring, this is the base. Actually, sorry, f of W, which is f of W modulo W square minus 1. Then, since we can manage this one, this copy, these are the code words over this ring, we can say, we can understand the larger one, which is copies, for only 3 copies of this one. So we can answer the original problem, or the original ring that we were interested in the beginning. So one can look on similar distance work. As I said, the generators had odd degree over there. What if they have even? What can we say? We can work at different sizes. That's fine. Different rings are also, and this is what's happening nowadays. We're looking for different rings. But as I said, the gray map had to satisfy the relation between the ring and the DNA code. Okay, and also DNA code with best possible parameters, even I should say, for the DNA case, or the properties, 2 properties for rings, we don't have a bound. It's an interesting question to find a bound to tell how good they can be. Okay, and regarding the metric itself, we still, there are works, but with this one specific or similar rings, there are different metrics, different distances that can be worked on. I think this is it, and thank you for your patience, for all of you in this very difficult time. And also I would like to thank the organizers, and especially Professor Dr. Rashid Farouk for his kind invitation. It was interesting in this specific hard time.
Thank you, Professor Irfan Shiab, for this wonderful talk. And now, audience may ask questions.
Yeah.
Any question, please? So if there is no question, I thank again Professor Irfan Shiab.
Thank you.
Now our next speaker is Dr. Tariq Javed from International Islamic University. The title of his talk is Spectral Methods for Boundary Layer Flow Problems. Dr. Tariq Javed. Dr. Tariq, can you hear me?
Well, yes, Assalamu alaikum.
Walaikum salam.
Yes, may I start my presentation?
Yes.
Yes,
Please share the slides.
the previous speaker is there, I can't share my screen because Zoom says you cannot start screen share with other participants sharing.
Professor Irfan, can you please stop share your screen? Dr. Tariq Javed, now you
Yes.
may proceed.
Yes, I'm coming. I'm available to everyone. Am I available to everyone
Yeah.
now?
Yes.
Okay. Thank you so much. I'm Dr. Tariq Javed, Associate Professor from Department of Mathematics and Statistics, International Islamic University, Islamabad, Pakistan. My title of the talk is Spectral Methods for Boundary Layer Flow Problems. Actually, this talk is especially dedicated to all those people who have ever worked on the boundary layer flow problems or who have desired to work on these problems. So far, we have background of different analytical methods, like the previous year, one of the most famous perturbation method, Adomian decomposition method. This is the problem. This is the method where the linear operator is the higher order operator of the differential equation will work as the linear operator, and the rest of the equation will be set on the right hand side. And homotopy perturbation method gives little freedom as compared to the Adomian decomposition method. However, one of the most famous method which was very much used in last 2 decades by a number of authors in China and Pakistan and the rest of the countries. Homotopy analysis method actually gives us many way of freedom, like it provides us an auxiliary parameter to control the convergence of the series, and similarly it gives us freedom to choose the linear operator, which was bound in Adomian decomposition method to have only the higher order derivative be taken as the linear operator. However, the homotopy analysis method is quite flexible in providing these freedoms. Similarly, auxiliary function was also embedded in that method, which was very much helpful to achieve the convergence of the series. Later on, since the method was actually analytical function based method, it was based on series solution, and to obtain the higher order, to obtain the convergence of the solution, we need to achieve the more and more maximum order solution. For this, we need a lot of time to compute. For this, homotopy analysis method was delayed. In this situation, optimal homotopy analysis method was introduced by Shajan Liao again, which was given the few more methods embedded in the method, that how the best value of the auxiliary parameter can be chosen, where one of the most famous H cut was given as an auxiliary parameter, and optimal homotopy analysis method provides us that how one can choose the best value to achieve the convergent solution of any differential equation. After it, a number of researchers was also doing spectral methods. and Mozart et al. And a few other peoples have introduced combination of spectral methods and homotopy analysis method, in which the basic framework of the method was the same as that of homotopy analysis method, but instead of using the analytical function, spectral functions or numerical data was incorporated and named as spectral homotopy analysis method. On the other side, numerical methods are also available to compute the solution of the differential equation. Since everyone knows that the to represent the mathematics, to represent the flow of any fluid model, Navier-Stokes equations are normally utilized, and due to convective part in it, the equations are most of the time are converted or reduced into nonlinear boundary value problems. And homotopy analysis method and spectral homotopy, optimal homotopy analysis methods have all been used to obtain the solution of nonlinear boundary value problems. On the other side, numerical methods have also been used by a number of researchers. There are actually two methods in this situation. One method is convert your boundary value problem to a system of initial value problems. And after converting to the system of initial value problems, number of methods are also available to solve those initial value problems. However, to satisfy those, the extra or missing condition, shooting method or similar type of methods can be used to to achieve the accuracy accuracy at the terminal point. For this purpose, method of superposition, method of chasing, and method of adjoint operator, and one of the most famous shooting methods, which combines the RK method of any order with shooting algorithm. These all methods are used in the situation where boundary value problems are reduced into system of initial value problem. One can one can directly solve the boundary value problem as well if he doesn't want to convert the boundary value problem to the initial value problem. He has many options as well, like explicit finite difference schemes are available of different order. Implicit finite difference schemes, among them Keller box method have been extensively used to solve the problems relating to boundary layer flow problems. It is actually implicit finite difference scheme. And in the same category, spectral methods are nowadays very much in and can be used to formulate the solution of the problem. Actually, in all the numerical methods, the solution is always available at the grid point only. At the grid point only. For example, these are the two grid point solution, one and the second one. The solution, every numerical method will provide the data at these 2 points. However, no numerical method provides the data between these two nodes. In this situation, it means we lack the accuracy between the two nodes. If we increase the number of nodes, of course we will put burden on the computer, on the laptop, and this is the main hurdle of the numerical methods. In this situation, spectral methods have advantages, like through finite difference scheme, the values can only be known at discrete grid points. That the solution is provided only at the grid points. However, spectral methods help to find the values between the nodes too. It provides, and with greater accuracy, the solution between the two nodes. The second advantage is very much easy to use, very rapid, very fast, easy from programming point of view. Higher order accuracy between the two consecutive nodes can be achieved. Nodes are actually in this methods. Nodes are interpolated by using the Chebyshev, Legendre, or Fourier polynomials. Mean depends on the domain, depends on the boundary condition. You may opt to choose Chebyshev polynomial, Legendre polynomial, Fourier polynomials. Any of the polynomial can be used to represent the spectral matrix. The method which I'm going to explain is actually Chebyshev based spectral method. Chebyshev, first we need to define some Chebyshev points like xj defined by cos of j pi by n for j is equal to 0, 1, 2 up to n, which will be used to construct Chebyshev differentiation matrix. Now, first I'll explain that how the differentiation matrix can be made in the spectral matrix. For this, spectral differentiation is being explained, which will be used to construct Chebyshev differentiation matrix of order n plus 1 plus n plus 1. Consider for n is equal to 1, the interpolation polynomial will be, we will call it, because cos of j pi by n is the function. For j is equal to 0, you will get 1, and for j is equal to n, you will get minus 1. It means x naught is equal to 1 and x1 is equal to minus 1. And the interpolation polynomial and its derivative through data y0 and y1 written in Lagrange form. This is the Lagrange's polynomial. At the points x0 is equal to 1 and x1 is equal to minus 1. For x0 is equal to 1, we will get y0, that is p at 1. By putting x is equal to 1, we will left with p of 1 is equal to y0, and at x1 is equal to minus 1, p of minus 1 will be y1. It means x0 against y against x0 is y0, and y against x1 is y1, and one can take the derivative like this: p prime y0 by 2 minus y0. By this formula p prime of x, one can generate the D1 matrix. The formula implies that D1 is the 2 by 2 matrix whose first column contains the constant entry 1 by 2 and whose second column contains the constant entry minus 1 by 2. Actually 1 by 2 is due to this coefficient of y0, and minus 1 by 2 is the coefficient of y1. This is how the Chebyshev spectral differentiation matrix of order 2 by 2 can be obtained. In the similar way, now consider n is equal to 2. If mean we have three collocation points, the interpolation points are x0 is equal to 1, which was evaluated by using x is equal to cos of j pi by n. X0 is equal to 1, x1 is equal to 0, and similarly x2 is equal to minus 1. By using the same methodology of Lagrange's polynomial, we computed the polynomial p of x is this, which is against x0 will be y0, x1 will be against x1 will be y1, and again x2 will be y2. By taking the derivative of this p of x, we get p prime of x. The differentiation matrix D2 is the 3 by 3 matrix whose jth column is obtained by sampling the jth term of this expression at by setting x is equal to 1. We will get coefficient y0 as 3 by 2, minus 2 as coefficient of y1, and coefficient of y2 as 1 by 2. In this way, we will get the first row of this D2. Similarly, at x is equal to 0, we will get the second row of D2, and by x is equal to minus 1, we will get third row of this differentiation matrix. It is no coincidence that the middle row of this matrix, that is 1 by 2, 0, and minus 1 by 2, contains the coefficient for central 3-point finite difference approximation. This is the coefficient of the central finite difference approximation. And the other rows are the coefficient of one-sided, meaning left-sided and right-sided, meaning forwarded or backward finite difference approximation. Mean we are accomplishing this differentiation matrix. It is similar to that of the formula developed in finite difference schemes. But in the similar way, we can obtain the differentiation matrix of order n. The coefficient of the coefficients are of Dn are represented in this matrix. Now we will check that how much accurate how much accurate this function, this differentiation matrix is. For this purpose, we have taken the example of y of x is equal to exponential of x sine phi of x. And for n is equal to 10, we take the derivative of this function by using the Chebyshev differentiation matrix, and the graphs of both the exact and as well as the numerically computed derivative are drawn. And we check the accuracy or error in u prime of x for n is equal to 10. It is lesser than 0.04. The error is lesser than 0.04. However, if we increase the number of nodes, interpolation points by up to n is equal to 20, we can achieve the order up to 10 raised to the power minus 10. The graphs are this graph represents the error. It means that the Chebyshev differentiation matrix is of greater accuracy. To check further, like this function y is equal to x cubed mod exponential of minus x square, I'm sorry, 1 over 1 plus x square and x raised to the power 10. We can see that if we increase the number of points like this function, 1 over 1 plus x square, between 40 to 50, the accuracy is of 10 raised to the power minus 15. Similarly, we can see the accuracy of the Chebyshev differentiation matrix of all these functions given here. By applying the similar procedure, we obtain the solution by using the same method of this linear boundary value problem. One can see that this is the exact solution of the differential equation. The error is actually up to the 10 raised to the power minus 10, that is exponential of minus 10. Similarly, if we apply the method to this non-linear boundary value problem, we have achieved the accuracy of 15 decimal places with that of the exact solution by only choosing n is equal to 29 number of grid points. It means that the spectral methods are very good and they are highly accurate. Now the question is that how one can move with the partial differential equation. Here we use the canonical product, like if 2 by 2 and the canonical product of two matrices will be written this. For this purpose, since we have equations uxx plus uyy is equal to Poisson equation, some function, and u is equal to 0 on the boundary, and to represent uxx and uyy, we convert this operator like canonical product of identity of dn square into dn square into I, which will be computed by like this as shown in the picture. By applying the same procedure and the boundary conditions, we computed the solution, which is again up to 9 decimal, which is accurate up to 9 decimal places. Solution of the Poisson equation, the results has been interpolated to find a rectangular grid for plotting. The computed value is accurate up to the 9 decimal places. We have developed, and the solution is checked actually at the point u at 2 raised to the power and u at under root 2 and under root 2, that is x equal to under root 2 and y is equal to under root 2. This is accurate up to 9 decimal places. But most of the problems in boundary layer flow actually they have infinite domain. But the problem is that with the spectral method that it contains domain between -1 and 1. To tackle those boundary layer problems, we need to reduce the boundary value problem into the finite domain. And for this purpose, one can use the transformation xi is equal to 2 over eta maximum into eta minus 1, where eta maximum is infinity. But by using this transformation, we will bring our problem to the confined domain, which will be between -1 and 1. And and rest of the method will be same. And in this way, one can achieve the solution of all boundary layer flow problems which have infinite domain. It means so far we have seen that the spectral methods are very good for not only linear boundary value problem but also non-linear boundary value problem, comprising of differential ordinary differential equation, but also for the partial differential equation. But in the similar way, if the problem is time dependent, we can use these methods as well by using this. Like for space derivative, Chebyshev differentiation method dn will be used, and for the time derivative, an appropriate finite difference scheme must be utilized. Or even one can solve the problem by shooting method at time steps. In this way, by using space derivatives and time derivatives, one can achieve the solution of all boundary value problems having time derivative or time function as well. This is one of the example I have chosen to display you the accuracy of these methods for all for problems of boundary layer flow. This is the problem of the fluid flow through convergent or divergent channel under the effect of constant magnetic field. The mathematical model, which was actually Navier-Stokes equation, and then by using similarity transformation, it was reduced to an ordinary differential equation, a non-linear ordinary differential equations, and the boundary condition of this flow problem is f at +1 is ±1 is 0, and f at 0 is equal to 1. This is the boundary condition of the problem, and by applying the same procedure as I've explained so far, we have achieved the solution. Like this is the method that this is the procedure that how one can achieve the solution that f of beta, which is to be known, will be represented as a series like this an tn, that is a naught t naught plus a1 tn up to an tn, where tn are the actually Chebyshev polynomial. Here one can alternatively choose other polynomial as well. It means these functions will be available between every two. These functions will work as the connector between two nodes, which was not given in the rest of the numerical methods. Here, these functions, these polynomial, Chebyshev polynomial, Legendre or hypergeometric function, these will be provided, or these will be helpful as a solution between the two nodes. Here, in this method, we have computed the coefficients a naught, a1 up to an, and by reducing this differential equation to the system of linear algebraic equation, by using any of the method, like which reduces the non-linear problem to the linear problem, and by using any of the matrix algorithm, one can achieve the solution of linear algebraic equation. And in this way,
Dr.
one can,
Tariq, sorry to interrupt. You have just 2 more minutes to complete the talk.
inshallah, so I'll complete within time. In
Thank
this
you.
way, we can achieve the coefficients an, and this will work as the solution of the differential equation. One can say that it is a combination of numerical and as well as the analytical method, where f of beta is actually the analytical function. The results are drawn to show you the solution for different real numbers, for different Weissenberg number, and for different Hartmann numbers. Right. These are the books which can be used as a reference book to see or to learn these methods. One of the most, John P. Boyd, and similarly M.Y. Hosseini. These books can be used for further explanation. Thank you so much. Thank you.
Thank you, Dr. Tariq Javed, for a wonderful talk. Now, audience are requested to ask questions.
Professor Mustafa Turk Yilmazov, you may ask questions, sir.
Thank you, Dr. Javed, for this nice talk.
Thank you, sir. Thank you.
Well, as you said, spectral methods are quite accurate methods, and it can be applied to partial or ordinary differential equations successfully. But it has also disadvantages, you know. One of the disadvantages is
Dr.
that
Asif, please mute your mic.
I am sorry, I can't listen to your question, sir. Please.
can you hear me now?
Yes, yes, yes. Please.
Yeah, well, as I said, spectral methods are very powerful methods which can be applied to solve accurately differential equations of any order anyway. But you didn't mention any disadvantage of such methods, because see, there are scholars here who want to know what are the disadvantages, you know, main disadvantages. So according to your experience, what are the disadvantages of this method anyway?
Actually, what I faced as a disadvantage is two major disadvantages are there, that one can achieve the accuracy up to achieving only up to 50 grid points. If we increase the grid points in this method, I face that the solution remains divergent. I don't know what is the reason behind this. For this purpose, we normally use 30 to 50 number of grid points to achieve the accuracy.
Let me explain that for you, because see, those Chebyshev differentiation matrices are dense matrices. So if you try to invert the resulting matrix system, you will have troubles. You cannot invert a huge matrix easily. See, because this is dense matrix. So if you try to invert, you will get a numerical, you know, instabilities. That's why you cannot increase the number of nodes from 60, maybe 60. Yeah, I also used this method a long time ago. 64 nodes are, you know, quite effective, but more than that, you hit the unstable numerical instabilities. Yeah. Another disadvantage is that, you know, it's not easy to deal with nonlinear terms. So you have to linearize somehow such terms. So what sort of linearization you use?
I use quasi-linearization scheme, Newton's method. Quasi-linearization scheme I use. But as far as my experience is concerned, one can invert those matrices by either using the linear system of equation, or otherwise one can achieve the solution by using the nonlinear algebraic equation as well. Non-linear system of algebraic equation, but only up to using a fixed, that is n is equal to 50 or 60 number of grid points.
Yes, exactly. Yes.
Yes, and similarly, there are many disadvantages of this method as well, because this is not method for all boundary value problems. Actually, like you must have a regular domain, as many of the differential equations have to be solved on irregular domains, are different shapes of the domain, and for these situations, spectral method will not work. And in this situation, we need to move with the finite element analysis or finite element methods in combination of spectral methods.
Okay, thank
yes,
you.
In all those problems, one is to go to the finite element methods, where spectral method will not work.
Okay, thank you very much.
Thank you, sir. Thank you.
Is there any other question? So if there is no question, I thank again Dr. Tariq.
Thank you so much, sir. At the end, I would like to thank Dr. Rashid Farooq, sir, Dr. Mirad Mustafa, sir, Dr. Mohammad Qasim, sir, and you, sir, Mujibur Rahman, sir. Thank you so much for inviting me at this conference.
Thank you.
Welcome.
Now, our next speaker is Dr. Tahir Mahmood from International Islamic University, Islamabad. So the title of his talk is A Novel Approach Towards Bipolar Soft Sets and Their Applications. Dr. Tahir Mahmood.
Assalamu alaikum, dear friends.
Walaikum salam.
Are you seeing my screen, please?
Yes, yes.
Okay, I start my presentation with the name of Almighty Allah. It is my pleasure and honor to present my work in front of very well-known mathematicians in NUST e-conference on recent trends in mathematical sciences. The title of my talk is A Novel Approach Toward Bipolar Soft Sets and Their Applications. The table of contents of the talk are, the first of all, we will discuss introduction, then preliminaries and the motivations, and next T bipolar soft sets. In the next section, we will discuss the algebraic structure associated with T bipolar soft sets. And in the section number 5, we will discuss decision making based on T bipolar soft sets. And then we will discuss conclusion and some future direction. And in the end, I will present some important references which I used during my talk. Okay, to handle the uncertainty, has always been a problem for the researchers and decision makers, as it appears in almost every field of real life problems. Many efforts have been made to cope with it, to concern. Excuse me. Okay, thank you. The first compact attempt in this direction was made by Zadeh when he familiarized the notion of fuzzy sets in 1965. In 1982, Pollock familiarized the notion of rough sets. Although these theories have their own advantages and these theories proved their effectiveness, but the theory of soft sets by Molstov in 1919 did spade work as it generalizes both the theories. Maggi et al. Furnished some operations to soft sets which later on improved by Eli et al. The applications of soft sets in decision making was initiated by Maggi et al. In 2002. Since then, many other authors contributed in this direction. For example, Kagman and Inglou and Kong et al. Did numerous work in the applications of soft sets in decision making. The notion of fuzzy soft sets was introduced by Maggi et al. Roy and Maggi toiled on fuzzy soft set theoretic approach to decision making problems. The notion of bipolar valued fuzzy soft sets was initiated by Lee in 2000. Abdullah et al. Comments the perception of bipolar fuzzy softs and pragmatic this perception in decision making problems. In 2013, Shabir and Naz instigated the idea of bipolar soft sets, and then keeping this concept in view, Naz and Shabir familiarized the idea of fuzzy bipolar soft sets and studied their algebraic structures and their applications. In 2014, Karsan and Karatas espoused a different methodology to introduce bipolar soft sets. If we sum up all the above debate, then we postured that keeping in view the association between fuzzy sets and soft sets, and keeping in view the significance of bipolar valued fuzzy sets, two attempts have been made to define bipolar soft sets, one by Shabir and Naz and the other by Karsan and Karatas. But if we notice, then we come to know that in both approaches, the conception of bipolar soft sets has some shortcomings, which we will discuss in our upcoming sections of the talk. So keeping this downside of the defined bipolar soft sets, in this talk, we have embraced a new approach to define bipolar soft sets and we named it T bipolar soft sets. Rest of the talk is arranged as follows. In section 2, we have given some basic definitions to make the talk self-contained and to justify, to redefine the notion of bipolar soft set. In section 3, the notion of T bipolar soft sets is familiarized, its basic operational laws are given and related results are conferred. In section 4 of the talk, some algebraic structures are discussed associated with new defined T bipolar soft sets. In section 5, some applications of T bipolar soft sets towards decision making are discussed. In section 6, conclusion of the work presented is drawn and some future directions are discussed. Preliminaries. In this section of the talk, we have given some basic definitions to make the presentation self-contained and for the motivation to define T bipolar soft sets. First, see the definition of a fuzzy set. Let A be a non-empty set, then a fuzzy set in A is characterized by a membership function f from A to unit closed interval 0, 1. Next, we have the definition of a soft set. Let A be a non-empty set of parameters and U be an initial universe, then a soft set fa over U is characterized by a set valued function f from A to power set of U. Next, we have a definition of intuitionistic fuzzy set. Let A be a non-empty set, then an intuitionistic fuzzy set in A is characterized by two functions f from A to unit closed interval 0, 1 and G from A to unit closed interval 0, 1, where f is called a membership function and G is called a non-membership function. The condition that the sum of the values of f and G must belong to 0, 1 is the part of the definition of intuitionistic fuzzy set. Next, we have a definition of double-framed soft set. Let A be a non-empty set of parameters and U be an initial universe. Then a double-framed soft set over U is characterized by two set-valued functions f from A to power set of U and G from A to power set of U. Next, we have a definition of bipolar valued fuzzy set. Let A be a non-empty set, then a bipolar valued fuzzy set in A is characterized by two functions f from A to unit closed interval 0, 1 and G from A to the closed interval starting from -1 to 0, where for some x belonging to A, f of x denote the satisfaction degree of the element x to the property corresponding to the bipolar valued fuzzy set, which we denote by FGA, and further G of x denotes the satisfaction degree of x to some implicit counter property of the bipolar valued fuzzy set FGA. Next, we have the definition of a bipolar soft set defined by Shabir and Naz. Let A be a non-empty set of parameters, then negation A consisting of the elements of the negation elements of the elements of A denotes the not set of A and U be an initial universe. Then a bipolar soft set denoted by FGA over U is characterized by two set valued functions f from A to power set of U and G from negation of A to power set of U, such that for all x belonging to A, f of x intersection G of negation of x is empty. Next, we have the definition of bipolar valued fuzzy soft set by Carlson and Karatas. It states that let A be a parameter set and A1, A2 be 2 and A1, A2 be subsets of A, such that A1 union A2 is equal to A and A1 intersection A2 is equal to phi, then the triplet FGA is thought to be a bipolar soft set over U, where F and G are set valued mappings given by F from A1 to power set of U and G from A2 to power set of U, such that f of x intersection G of f of x is equal to empty. Now, we have the remark, actually this remarks define the motivation that how it was necessary to define the new definition of bipolar soft set. Look here, from above definitions, we notice that The definition of fuzzy set and the definition of soft sets have some same characteristics in the sense that both are characterized by single valued function, both have a single set as domain set, both have a single set which is a lattice in either case as codomain set. The second remark is the definitions of intuitionistic fuzzy sets and the double framed soft sets have same characteristics in the sense that both are characterized by two functions, both have a single set as domain set for both the function, and both have a single set which is a lattice in either case as codomain set. Number 3, but this is not the case for bipolar valued fuzzy sets as compared to the definition of bipolar soft sets defined in 37 and 39. All this dialogue demonstrates that the space to define bipolar soft set has not yet been filled, as every definition in mathematics has its own importance, and it doesn't mean that the already existing definitions of bipolar soft sets are of no use, and the proposed definition of bipolar soft sets will nullify the existing definitions. But the purpose to redefine the notion of bipolar soft set is, one, to elaborate the notion of bipolarity in soft sets more effectively, and the other is, as there is up to the best of our knowledge, no such type of situation is discussed in soft sets earlier. From now onward, E will denote a set of parameters and A, B, C will denote the subsets of E, and U will denote an initial universe. Next, in this section, we will discuss T bipolar soft sets. In this section, we familiarize the perception of T bipolar soft sets. We will delineate binary operations for T bipolar soft sets, and we will also deliberate some basic properties and some results commitment with these concepts. First, we contemplate the succeeding examples. Let us consider the case where a researcher, Dr. Shabir, wants to submit his 4 research papers, A2 on fuzzy sets, A3 on soft sets, and A4 on rough sets, research journals. For the purpose, he has to propose some potential referees, and also he has the option to propose some referees, to oppose some referees. Keeping in view all the aspects, he prepared a set X of some proposed as well as a set Y of some referees to oppose. Hence, in this case, he has under consideration the set U consisting of elements of the set X and elements of the set Y of all referees. For each of this article, he selects some referees from X to propose and selects some referees from Y to oppose, keeping in view all the aspects of the article. A1 on homological algebra, he decided to propose X2, X3, X4, and he opposed Y1 and Y2. Similar, he proposed and opposed for his article from A2, A3, and A4. Note that all this information can be modeled mathematically as this one. Here it can be perceived that both the functions f and g has common domain A. Codomains of f and g has nothing in common except the set phi. Further, we notice that same is the case in bipolar valued fuzzy sets. Hence, we have the following definition. Let E be a set E of parameters, A be a subset of E, U be an initial universe, and X be a proper set of U, and Y is the complement of X in U. Then a triplet FGA is said to be a T bipolar soft set over U, where F and G are set valued mappings given by F from A to power set of X and G from A to power set of Y. In this case, we write FGA is equal to A, F of A, G of A, where F of A belongs to P of X and G of A belongs to P of Y. Or simply, FGA can be represented by this notation. The collection of all T bipolar soft sets over U is denoted by this notation. The remark 2, let A equal to A1, A2, A3 up to AL be a subset of E. X is equal to X1, X2, X3 up to XM, y is equal to y1, y2, y3 up to yn, and FGAB corresponding T bipolar soft set, then we can represent FGA as the following table. Where zeta ijk is equal to the ordered pair mu j nu k, and mu j nu k are defined by this one, and further zeta star ijk is equal to mu j and zeta circle ijk is equal to nu k. Next, we consider another example to discuss some motivations to T bipolar soft sets. A university wants to appoint a permanent faculty member from the set A of visiting faculty members. For the purpose, the university authorities constitute two panels, X and Y, of experts, where panel X consists of members from outside the university and panel Y consists of members from inside the university. For each member of the panel X will decide about each publication and number of conferences attended, etc. While each member of the panel Y will decide about each candidate by considering his or her regularity and punctuality, attitude towards other faculty members, and behavior with students during class. Now the university authorities decided the selection criteria that towards each candidate, each member of the panel X will have to select a candidate by keeping in view his or her positive points, while each member of the panel Y has to reject a candidate by keeping in view his or her negative points. According to the decisions taken by the members of the panels X and X, the experts X1 and X3 are in favor to select the candidate A1, while X2 and X4 decided to remain neutral for the candidate A1. Similarly, the decisions taken by the members of the panel Y, the member Y3 is not in favor to select the candidate A1, while Y1 and Y2 decided to remain neutral for the candidate A1. Hence, for the candidate A1, the situation can be modeled as this one. Now, keeping under consideration the decisions taken by all the members from the panels X and Y, the result can be modeled mathematically as given in the following T bipolar soft set. So, result can be modeled by this way. And the tabular form of this T bipolar soft set FGA is shown in this table too. Definition: let F1G1A be a T bipolar soft set over U, then F1G1A is said to be T bipolar soft subset of F2G2B if A is subset of B for all A belonging to A, F1A is contained in F2A, and G2A is contained in G1A. Then we write F1G1A is subset of F2G2B. F1G1A and F2G2B are said to be equal if and only if F1G1A is subset of F2G2B and F2G2B is subset of F1G1A.
Dr. Tahir, you have
Yes.
2 minutes to complete the talk.
Dear sir, whether okay, here we have defined the complement. Next, we have defined the AND and OR product. And here we have discussed the De Morgan's laws. Here we have discussed the extended union of the T bipolar soft sets and extended intersections of the T bipolar soft sets. Here we have the corresponding proposition. Here it is discussed that for the T bipolar soft set, the distributive law is not necessary to hold. And here in this example, we have shown that for the extended intersection and extended union, the distributive laws does not hold. Here we have discussed the restricted union and restricted intersection for T bipolar soft sets. And here we have the corresponding proposition for restricted union and restricted intersection. Now we discussed some algebraic structures associated with T bipolar soft sets. Here it can be seen that if delta belongs to this set, then this collection is a commutative semigroup whose every element is idempotent. Here T bipolar soft sets with restricted intersection, restricted union is a commutative semi-ring. It follows from proposition 2 and remark 3 that T bipolar soft sets with extended intersection, restricted union is not a semi-ring. However, if we define on set A, then it is a commutative semi-ring. Here we have discussed some decision-making problems without weights and with weights. For this, first we discussed score functions. Here is the algorithm. Here the tabular form for the example 2. By applying the score values, we have the table 4, and it can be seen that according to the algorithm 1, the candidate A2 will be selected. Sometimes in decision making, some decision makers have less importance as compared to other decision makers. For example, to decide about admission policy of a school, a meeting was called in which 4 persons participated, which were school owner, school principal, school vice principal, and accountant of the school. Now, here it is clear that all the decision makers have not the same weightage. So in decision making, the weightage of a decision maker also matters a lot. So here now we establish an algorithm to handle a decision making problem in the presence of weights. In this example, we have used the weights functions for decision making. Now here, after the involvement of the weight functions, the candidate A1 will be selected. According to Zoo, the weight vector WO can also be calculated as this one. And we repeated the example 5 by calculating the weights by using these formulas. Then we have the following result. And we notice that the candidate A2 has the greatest value, so it means it will be selected. Keeping in view the shortcomings in predefined notions of bipolar soft sets, in this talk we have defined and discussed the notion of T bipolar soft sets. Then running to new definitions, we have defined different binary operations for T bipolar soft sets, and then we have conferred some results associated with these binary operations. We evidence the existence of bounded lattices and De Morgan algebras interrelated with these binary operations. We also established some algorithms to solve decision-making problems and then solve the problem from daily life by using these algorithms. In future, this work can be extended to its application in algebraic structures and in rough set theory. Here are some important references which we used during this presentation. Thank you very much. Any question, please?
Thank you, Dr. Tahir, for a wonderful talk.
It's my pleasure.
Now
Sir.
questions from audience. So if there is no question, I thank again Dr. Tahir Mahmood.
Thank you very much.
Our next speaker is Mr. Rashid Iqbal from KUST, Kohat, Pakistan. The title of his talk is Symmetry Analysis and Conservation Laws of a Generalization of the Kelvin-Voigt Viscoelasticity Equation. Ji Rashid Iqbal, can you hear me? Okay, please share your slides.
Sir, I am not Rashid Iqbal. I am Zubair Hussain.
Zubair Hussain. Okay, Rashid Iqbal is not here. Okay, I repeat again. So Mr. Zubair Hussain is presenting now. The topic of his talk is a novel population initialization strategy for accelerating Levy flights based multiverse optimizer.
Yes, sir. Uh, good afternoon, honorable chief guests, professors, dear colleagues, and organizers and speakers. Assalamu alaikum.
Walaikum
Welcome
salam.
to welcome to e-conference entitled Recent Trends in Mathematical Science 3. And I would like to thank you for sparing your time and listening to me. I am Zubair Hussain, a student of PhD, Department of Mathematics, Abdul Wali Khan University, Mardan. The topic of my work is a novel population initialization strategy for accelerating Levy flights based multiverse optimizer. In this presentation, we will go through contents in which first I would like to discuss a brief introduction to economic load dispatch problem, multiverse optimizer or simply MBO, then Levy flight based MBO, then our proposed strategy, that is ILF MBO, then some experiments and results, then conclusion, and finally some references. So in this slide, I would like to present a brief introduction to economic load dispatch problem. As we know, in a practical power systems, all power plants are so far from the center of their loads and their fuel costs are different. Under normal operating conditions, the generation capacity is more than the total demand and losses. Therefore, there are many options for scheduling generations. As we can see in this figure, which is depicting a 24-hour demand versus time, from midnight to morning, cheaper fuel types can be used to fulfill the demand. On the other hand, in peak hours, that is from afternoon to midnight, expensive fuel types are added to fulfill the demands. The economic operation can be subdivided into two parts. In the first part is problem of economic dispatch, and second part is the problem of optimal power flow. Problem of economic dispatch deals with determining the output power of each plant to meet the specified load in such a way that overall cost is minimized. On the other hand, the problem of optimal power flow deals with minimum loss delivery where the power flow is optimized. For a mathematical problem, we need an objective function. So as I have discussed earlier, that the goal of the economic load dispatch problem is to minimize the total generation cost. So to simplify the optimization problem and facilitate the application of optimization techniques, cost function of generation units are simply modeled by a smooth quadratic function which can be written in this form. In this equation, CT is the total generation cost. This NG is the total number of generation units, and alpha, beta, gamma are the cost coefficient of the ith unit. And this PI is the actual power of output of the ith unit. Constraints. So A limitation or a restriction on objective function in design variable are called constraints. So for this problem, we have selected two constraints. Number first, that is power balance constraint. Power balance constraint can be defined as the total demand is equal to the sum of the power demand and power losses, where these power losses can be calculated by these equations. In this equation, these coefficients are taken from the literature. The second constraint is the generation limit constraint. So the output power of each generating unit has a lower and upper bound so that it lies in between its lower and upper bounds. The constraint can be represented using this. In this equation inequality, the P minimum is the lower bound and the P maximum is the upper bound of the ith generating unit. Now in this slide, we are going to present multiverse optimizer. So let me start from the beginning. According to the Big Bang Theory, our universe begins with an explosion of space itself. Starting from extremely high density and temperature, space expanded, the universe cooled, and the simplest elements formed. Then, other than this universe, there are many other universes called multiverse. So the multiverse is a hypothetical group of multiple universes. Together, these universes comprise everything that exists, the entirety of space, time, matter, energy, information, and the physical laws and constant that describe them. So in multiverse, there are some terms. Number first is a black hole. A black hole is a region in space having strong gravitational force such that nothing can escape from it. Even light cannot escape from this region. Then another term is a white hole. So a white hole is a hypothetical region of space-time which cannot be entered from the outside, although matter and light can escape from it. In this sense, it is the reverse of a black hole. And the third term is wormhole. So a wormhole is a speculative structure linking disparate points in space and can be visualized as a tunnel with two ends at separate points in space-time. So in 2015, Mir Jalili was inspired from the multiverse theory. He developed a technique called multiverse optimizer, and this algorithm is based on that multiverse theory, which consists of three facts: white hole, black hole, and wormhole. These white hole and black hole were utilized to explore the search space, and the wormhole help MU exploit the search space. So when wormholes stochastically generate a number of universes around a best so far universe achieved over a course of iteration, the MU is likely to get trapped in the local optima. So to remove the ambiguity and to improve the global search ability of the MU and enhance the ability to escape from local optima, MU is updated with Levy flights. In this slide, we are going to present our proposed strategy. So having an initialization process with the random generation of candidate solution will not be an effective idea in every case, especially when the search space are very large. So hence we have updated the LFMU by dividing the capabilities of the algorithm into two phases. In the first phase, the algorithm begins with a fixed random population for a certain number of function evaluations. In the second phase, the algorithm is focused on the best so far spots found during the earlier evaluations. So this strategy is shown to be very efficient in getting the best results with least number of function evaluation and time, and provide results of high quality. Then to check the performance of the proposed algorithm, we have selected 4 standard case studies of the economic dispatch problem with smooth quadratic function and their constraints. So each will discuss in the following sections. Case study 1. We have selected this case study with 3-unit power system with 600 megawatt. And the values for the alpha, beta, gamma, and B coefficients have been considered from the literature. The objective function can be written as in this form: C1, C2, and C3. And their constraints can be written as this in this form, that P1 lies between 35 and 210, P2 lies between 130 and 325, P3 lies between 125 and 315. This slide presents 2 tables, where table 1 presents the solutions of our proposed algorithm for case study 1 and compared our solution with state-of-the-art techniques, that is Firefly algorithm, Ant-line optimizer, and Liu-Flight-based multiverse optimizers. So which shows that our technique provides solutions of high quality with minimum losses, that is 17.1. And table 2 presents the generation cost and computational complexity for various algorithms and compared to the rest of the techniques, which shows that our proposed techniques provide solutions with minimum generation cost and with minimum time. Case study 2. We have considered a 6-generation unit system with 800 megawatt in this case study. And the objective function for this case study can be written as C1, C2, C3, C4, C5, and C6. Their upper and lower bounds rather than constraints can be written in this form: P1, P2, P3, P4, P5, and P6. Table 3 presents the solutions of our proposed algorithm and compared our solution with the rest of techniques, that is particle swarm optimization, Firefly algorithm, Ant-line optimizer, and Liu-Flight-based multiverse optimizers. And which shows that our proposed algorithm provides good solutions with minimum loss, that is 23.65 as compared to the state-of-the-art algorithms. And table 4 presents the generation cost and CPU times for various algorithms, and again which shows that our proposed technique provides high quality solution with minimum generation cost and minimum CPU time. So it is obvious from the given convergence plots that convergence speed of ILFMU is significantly improved by adding the novel adaptive initialization strategy. These plots are depicting the solution obtained during solving the case study 1 and case study 2. In both cases, ILFMU is quickly approaching to the best solutions. Case study 3. So in this case study, we have considered a 20-generation unit with 2500 megawatt, and their objective function can be written as in general form like this. And the values for alpha, beta, gamma can be considered from the literature. So this slide presents their unit operating ranges rather than we can call it constraints. That is, it is a 20 generation unit, so P1, P2 up to P20. This slide presents the solutions provided by our proposed algorithm and compared with the other techniques, that is biogeography based optimization, lambda iteration, and harmony search, entline optimizer, leaf light based multiverse optimizer, and which shows that our technique provides the solution of high quality with minimum transmission losses, that is 85. And table 6 presents the generation cost and CPU times for the various algorithms, which dictates that our proposed strategy provides solution with good quality, with minimum generation cost and minimum CPU time. Now, this is the final case study that we have considered of 1200 megawatt and 6 generation unit. Their objective function can be expressed as C1, C2, C3, C4, C5, and C6. Their
Zubair, you have 5 minutes to complete the talk.
Operating ranges can be presented as P1, P2, P3, P4, P5, and P6. So we have compared our solutions with the state-of-the-art techniques in table 7, that is genetic algorithm, particle swarm optimization, evolutionary structural optimization, differential evaluation, harmony search, hybrid harmony search, and leaf light based multiverse optimizer, which shows that our techniques provide solution of high quality with minimum losses, that is 7.035. And table 8 presents the generation cost and CPU times of the as compared to the other techniques, and which shows that our techniques provides high quality solutions with the minimum cost and minimum CPU times. So the conclusion of the current work is that we have improved the LFMVO technique by initializing it with an adaptive initialization strategy. The performance of our algorithm is significantly improved, and the exploration and exploitation capacity of the algorithm is balanced. So moreover, the quality of population is an important factor which can directly or indirectly affect the strength of an algorithm in searching the given domain for an optimal solution. So to remove this ambiguity, we have updated the leaf light based multiverse optimizer technique into 2 parts. In the first part, the algorithm initializes with a fixed random population for a certain number of function evaluation. In the second part, the algorithm is focused on the best so parts found during the earlier evaluation. So this study is shown to be very efficient in getting the best results with less number of function evaluation and CPU times. So to check the performance, the capability and competency of the proposed algorithm, we have selected 4 standard case studies of the economic dispatch problem, 1 with 3 units, 2 with 6 units, and 1 with 20 units. So our result show that the ILFMUO methods provide solution of high quality with less cost. In all cases, the performance of ILFMUO is comparatively better than the other algorithms. However, there are some references. Thank you.
Thank you, Zubair. Now question answer session. Audience may ask questions.
Yes, sir. Yes, sir.
So any question, please? If there is no question, I thank again to Mr. Zubair Hussain. So our next speaker is Mr. Muhammad Adnan Anwar from LUMS, Lahore, Pakistan. The title of the talk is Finite Element Simulations for Multi-Physics Problems. Muhammad Adnan Anwar.
Thank you so much. Assalamu alaikum. I am Adnan from Lahore University of Management Sciences. Working under the supervision of Dr. Mudassir Razak, I will present a brief discussion of what we are doing. I will talk about finite element simulation for incompressible fluid structure interaction and its applications to bioengineering and heat transfer. Okay, let's start the talk with the titles displayed on the screen. Finite element simulations for multiphysics problems with applications to fluid structure interaction, heat transfer, and hemodynamics. Let's start our talk by defining the term multiphysics. The real word is multiphysics in nature. Multiphysics is actually a phenomena that involves multiple physics. The word is multi in nature. Human body is multi in nature. If we see human body, it is complex. In fact, very complex. It has flows, it has elastic and porous part, it has almost solid part. So it is a mixture of many. Similarly, if we look around, we can see interaction of different physical phenomena. In short, more or less everything is interacting. One of the promising and demanding sub-branch of multiphysics is fluid structure interaction. Fluid structure interaction, as name stands, it is the interaction of fluid world and the solid world. Due to this interaction, solid goes under deformation. The variety of fluid structure interaction occurrence is abundant and ranges from huge tent roof to tiny micro pumps, from parachutes and airbags to blood flow in arteries, and many more. The best example to understand fluid structure interaction could be an automobile airbag, which goes under deformation when interact with the passenger. Too much deformation is obviously not required because in this case, it may lead to injury. Apart from airbag, it has application in aerodynamics, in submarine, underwater, in bioengineering, stent implantation, clipping, aneurysm, and cardiovascular are famous problems of fluid structure interaction. To solve a fluid structure interaction problem, one need to expert in interdisciplinary subjects. As I started learning from continuum mechanics, where I get understanding of basic concepts of kinematics. Then I moved to fluid mechanics to understand the basics of flows and their mathematical modeling, and then for solid mechanics, where I learned about different elastic materials and their constitutive relations, and finally got understanding of fluid structure interaction. Their real life application, particularly in hemodynamics, fascinating me to choose this field. After targeting an application, the first step is to develop a mathematical model of the problem and then discretizing using finite element method, then coding and its implementation to get the results of interesting parameters. The last and for most important part is analysis of result. This is the way we tackle a problem in fluid structure interaction. Here is the layout of what is coming in the next slides. In next few slides, I will talk about modeling from large deformation, ALE formulation, which will be followed by numerical tasks involved, space and time discretization, and some examples are projects which we have accomplished. Lagrangian, Eulerian, and arbitrary Lagrangian Eulerian descriptions. These are the kinematic descriptions which are related to the motion of particles. Here, the triangle sign represents the material point and circle represents the mesh nodes. In Lagrangian description, each individual node in the computational mesh is permanently connected to the associated material particle during motion. This can be described as if you are sitting in a boat, followed a current, and you are having the same speed as that of water. You are studying the same particle at different times at different places. This method is mainly used in structural mechanics. Eulerian motion. In Eulerian motion, the mesh is fixed and the continuum moves and deforms with respect to computational mesh. This can be described as if you are standing in the water and the current is passing you by. You are studying velocities, pressure at different time at the same place. This method works well for large deformation and is often used when working with fluid computations. The third one is arbitrary Lagrangian Eulerian description. ALE description is more general description that embeds the advantage of the two descriptions discussed above. In this description, mesh nodes may be fixed or move in prescribed fashion with the continuum or relative to the continuum, but mesh is allowed to move independently. Deformation of the solid part is described by the mapping chi s with corresponding displacement and velocity, and due to continuity across the interface, we can define global quantities on omega. This is the reference domain and this is the current domain. And the deformation of fluid is noted by the chi f. And the mathematical model for the structural part is given here, and for fluid part is given here. These are the governing equation for structural part and for the fluid part. Governing differential equations are based on balance laws for mass and momentum and completed by constitutive relations for the fluid and solid phases, as well as their mutual interactions. We use no-slip boundary conditions for our simulations, and the Dirichlet boundary condition is prescribed for the solid displacement at the boundary part gamma 2, and the stress-free boundary conditions for the solid is applied at the part of gamma 3. The arbitrary Lagrangian Eulerian is a finite element formulation in which the computational system is not a prior fixed in space or nor attached to materials as it is in Lagrangian description. Here are some characteristics of Lagrangian description and Eulerian descriptions. This equation is written in ALE formulation, and we can recover Lagrangian description and Eulerian description from this ALE formulation. In Lagrangian description, mesh nodes are not fixed, and it is best suitable or best workable for structural mechanics, and mesh is tangible and it is expensive. In Lagrangian description, mesh nodes are fixed and it is more suitable for fluid mechanics. It can handle large deformations. And the disadvantage of Eulerian description is that there may be instability due to convective term. This is the complete system of fluid structure interaction in ALE formulation. This is the momentum equations. This is the continuity equations and boundary conditions. Fluid structure interaction problem solving approach can be divided into weakly and strongly coupled approaches based on the data exchange. The drawback of the partitioned approach is that the treatment of the interface and the interaction is often problematic. Although they are flexible, less programming effort required, but due to explicit nature of this coupling, convergence problems may often arise. Consequently, there is restriction on the choice of the time step even if implicit time stepping schemes are used by the two solvers. Contrarily, the strong coupling approaches are more difficult to formulate and to program. Normally, a simultaneous solution of the whole FSA problem necessitates reformulation of the system of equations and confines the choice of the numerical method to be applied. Additionally, special approaches may be needed for modeling the nonlinearities in each of the physical part. Valuable programming effort are required to create and validate a program applicable to wide range of problems. However, there are no approximation error and convergence problem in this approach due to data convey between the fluid and structure part. To discretize the nonlinear system of PDs, we use the P2 P1 finite element. In this finite element, the pressure variable are defined only on the vertex, and the velocity variables are defined on all vertex and the mid nodes. The P2 P1 interpolation is employed because the LBB condition is satisfied without any stabilizing tools. Stable means the resulting matrix is regular and we can solve the problem. So LBB condition says if we take the P2 P1 element correctly, then the matrix can be inverted. Here is the LBB condition for Stokes problem. This is a Stokes problem. We obtain the weak formulation, and this is the resulting matrix. LBB condition states that the saddle point problem is well posed if and only if below condition holds, and this condition is called LBB condition. And P2, P1 satisfy this condition, so there are no instability issues in simulations. After discretization in time and in space by the standard Galericon finite element method, we arrived at a set of nonlinear algebraic equations of the form. Here are unknowns and mass matrix and some others. S are the stress operators and C is the incompressibility. constraints for the solid, and B is the discrete gradient operator, and so on.
Adnan Anwar, you have 5 minutes to talk.
Okay, sir. Then solution of nonlinear problem. This method is similar to classical Newton method, but in addition, it has a term omega j, which is called damping factor. Of course, it slows down the convergence rate of Newton method, but main advantage of this is that it globalizes the Newton's local convergence. Since we know the sparsity pattern of the matrix in advance, which is given by the used finite element method, Jacobian can be computed by using finite difference from the residual vector R. The next are some examples are some projects which we have accomplished. The first one is discrete heating effect. Here we have our cavity, triangular cavity. This is a CFD problem. Here we have added both CFD plus FSI, both projects. This is a CFD type. We have a cavity and discrete heaters fitted on the midpoints of the triangle. The main aim was to study the average Nusselt number due to this discrete heating effect. This is also a CFD problem, CFD for aerodynamic reconstruction. This is also a cavity, and Newton equation was solved for Reynolds number 100 and 500. The objective was to study the upstream velocity, downstream velocity, drag, lift coefficients. Analysis of the resulting drag and lift forces acting on the obstacle with respect to the angle of attack of the upstream velocity and the Reynolds number is made in this study. A finite element method for these prototypical two-dimensional configuration are presented. This is a FSI problem. The upper wall is elastic and the fin is also elastic in some cases. Hydrodynamic forces like drag and lift coefficients for considering nonlinear elastic material models SVK, Neo-Hawkian, and Moni-Rivlin are evaluated separately. Besides, for a more physical insight into the problem, verification of the computed results is done by comparing the velocity, viscosity, pressure fields, and so on. This is also FSI problem. It has elastic walls. This is a stenosed bifurcated artery. This numerical study reflects the magnetic field's effect on the reduction of plaque formation due to stenosis in a stenosed bifurcated artery. The entire artery wall is assumed as linearly elastic and blood flow is modeled as Newtonian viscosity, incompressible, and biomagnetic fluid. The numerical results for displacement and velocity, magnitude, pressure, wall shear stresses for different Reynolds numbers are presented. The magnetic field reduces the flow separation, recirculation area adjacent to stenosis and give rise to wall shear stress. And that's all. This is a summary of what we have done. We have done some CFD problems and then some FSI problems. Thank you.
Thank you, Adnan. So audience are requested to ask questions, if any. If there is no question,
Professor,
yes, yes.
Professor Mustafa Turki Yilmazoglu, you may ask questions, sir.
Okay, Dr. Adnan, thank you very much for this nice talk.
Sorry, I am not a doctor. I'm a PhD student. Actually, a beginner learner, a beginner researcher.
Yeah, you are candidate for doctor anyway, so no problem.
Okay. Okay.
So I am wondering how you choose damping parameter in your iteration. You see, you just use damping parameter, damping factor, or what do you call it? That yeah, that omega there.
Yeah.
So how do you choose that damping factor? You just arbitrarily choose it,
No,
or just
using line search method.
are you fixing that to any arbitrary number, or is there an optimum value for that damping parameter?
I find omega by a line search method for different simulations. For example, if I'm doing some simulations, for that particular simulations, I first search for omega, where it gives optimal results, then I fix it.
Right. Okay, thank you.
Thank you, Adnan.
Thank you.
So our next speaker is Mr. Wahidullah from Kast Kohat, Pakistan. The title of his talk is Classification of Two-Dimensional Third-Order Nonlinear Cubic Ordinary Differential Equation by Complex Symmetry Method. Wahidullah Khan. Wahidullah, can you hear me?
Hello. Hello.
Ji Wahid, can you hear me?
Yes, sir. Hello.
Please share your slides.
Thank you, sir. Sorry, sir. Share करना.
After this talk, we have a photo session. So this photo session is of course online. Wahid, please share your slides. Wahid, can you hear me? So Wahid is facing some connectivity issue. Now we have a photo session. Ji, Dr. Qasim.
So now we
Everyone have to turn on their cameras, I think. Dr. Qasim.
डॉक्टर कासिम, इरफान शियाब नहीं है?
No, the Professor Irfan Shihab is here. I don't know. He just didn't open his video camera and just his mic is turned off.
So we conclude the session now. Thank you.
Kantasa, you are logged in from 2 computers.
Thank you, everyone.
We are closing the Zoom session now.
Thank you.
Okay. Kantasa, Isashiburi
Yes.
ne? Isashiburi ne? Genki deshita.